In today's video, I'll cover the basics of the ESP family of microcontrollers. I'll discuss the different versions currently available, some of the primary components found on development boards, then get into GPIO pin use. I'll talk about dealing with different voltages and discuss various ways to safely power your project. Finally, I'll cover a little bit about installing firmware or code onto the ESP8266 or the ESP32. Hi, and welcome to Resin Chem Tech. Now, I've done a lot of projects here on my channel that use the ESP microcontroller. Now, I might have an occasional project that uses an Arduino or Raspberry Pi, but the vast majority use an ESP chip. Why do I use the ESP? So today's video is for those of you who have never used an ESP or only used it to duplicate or clone other projects. As always, you can find additional information and links along with a link to a written companion guide for this video that will have copies of all the wiring diagrams, and you can find those links down in the video description. Let's start by looking at some of the key features and variations in the different ESP family of microcontrollers. First, it's important to understand a bit of terminology that might be a little confusing if you're new to working with microcontrollers. When referring to an ESP8266 or an ESP32, it really refers to the primary chip used, which is actually the large chip seen here. These are referred to as SoCs, or system on a chip, because they contain the processor, memory, input, output, really everything on a single integrated chip. To power and interact with the input-output channels of this chip, connections are made to these little tiny surface mount pins, which you can see on three sides of the ESP chip here on these boards. Now, it can be very difficult to solder wires to or even make temporary connections to a breadboard for testing. So as a beginner and likely even an intermediate, you probably won't work directly with the ESP chip. Instead, the chips are installed on a development or a breakout board. Now, these are identical ESP32 chips, but they've been installed on different types of development or breakout boards. Development boards take these tiny little pin connections and break those out into more convenient pins or through holes for connecting various components. Now, the development boards also offer a number of other features, such as a USB port for power and programming. You can even find specialty dev boards with features added for a particular type of project. There are dev boards specifically built for connecting a camera, for things like battery charging and monitoring for circuits with battery-powered projects, and even ones with built-in LCD displays. I'll cover some of the common dev board components shortly, but just understand that when someone references using an ESP8266 or an ESP32, they're most likely referring to a dev board containing the chip and not the actual chip itself. But before digging into the various development board components, let's talk about the ESP8266 versus the ESP32. In the beginning was the original ESP8266, initially released in August of 2014. There was primarily one model, although some future releases would make some minor revisions, more or less superseding the prior one. There were a number of different development or breakout board options, like the mini or versions with different numbers of pins or different types of connectors. The ESP chip family was primarily the same, with only minor differences between models. Then just 2 years later, in the fall of 2016, along came the ESP32. In addition to a faster and more powerful processor and more memory, it added Bluetooth, more GPIO pins, and much more flexibility with how these GPIO pins can be used. Since that original release of the ESP32, numerous additional series or models of ESP32 chips have been released. Unlike the ESP8266 models, the different ESP32 series aren't the same or similar as the various ESP8266 versions. As you can see from this chart, the different series of ESP32s can have substantially different features. First was the original ESP32, then a variety of other series were released, including the S series, C series, H series, and the newer P series. Unlike the ESP8266, in which the changes were pretty minor, there are some pretty big differences here, with some series offering things like Zigbee and others that don't have Bluetooth or even Wi-Fi. Unless you have a special need, the original ESP32 will suffice for most projects. So you have the original ESP8266 and multiple different series of the ESP32. Add in all the different types of development boards and you literally have hundreds of different options from which to select. How do you decide which one to use for your project? First, you need to select a chip and board that has the necessary number and types of features needed for your project. If you need your project to connect to Wi-Fi, then you probably wouldn't select an ESP32 H series or P series because they don't offer Wi-Fi and require additional components and complexity just to add Wi-Fi. If you're building a battery-powered device, you may want to consider a development board with a dedicated battery monitoring and charging circuit. Next, if installing pre-made firmware like Tasmota or maybe a certain GitHub project, you should always check the firmware or the project's documentation to see what type of ESPs are supported and to ensure you're using a compatible ESP board. Not all firmware written for the ESP8266 will run on the ESP32 and vice versa. But all other things being equal, I previously used and recommended the ESP8266. This D1 Mini was actually one of my favorite. This is because initially the ESP32 boards were 3 to 5 times the cost of the ESP8266. So for simple projects like maybe a temperature or humidity sensor or controlling a small strip of LEDs, spending the additional money for unneeded higher processing speed or features like Bluetooth that wouldn't be used was a bit of a waste. But over the past year or so, I've changed my recommendation to the ESP32 for a number of reasons. First, any cost differences between the ESP8266 and the ESP32 are now minor. In some cases and quantities, you may even find ESP32 boards cheaper than their comparative ESP8266 models. Next, many popular projects like WLED are slowly moving towards the ESP32, having already dropped support for some features like audio reactivity for the ESP8266. But probably most importantly, the ESP8266 was released in 2014. Espressif, the maker of the ESP chips, have pledged a minimum of 12 years of support and development for their chips. Well, the ESP8266 will turn 12 in 2026, meaning that the future development of the ESP8266 might stop. This doesn't mean your ESP8266 projects will stop working or that the ESP8266 can't still be used, but it does mean that everything is slowly moving towards the ESP32, and down the road at some point, libraries, code, and firmware may only work with the ESP32. So for the remainder of this video, I'll focus on the original ESP32, but many of the topics that I cover will also apply to the ESP8266 and other series of the ESP32, and I'll try to mention any major differences. Now let's take a look at some of the major components found on most development boards. It's important to understand these components as they can impact the different ways that you can power and communicate with the ESP. The largest single component on most boards will be the ESP chip itself, which I've already talked about. Now these two particular boards have an integrated Wi-Fi antenna, which works relatively well in situations with a good Wi-Fi signal, but may have issues in certain situations, like if the ESP was placed inside a metal enclosure, such as a mailbox or near other electrical components that could interfere with the Wi-Fi signal. For these situations, you can find development boards with a connection for an external antenna. Now, all current ESP chips operate at 3.3 volts, and since most of the GPIO pins are connected directly to the ESP, they also operate at 3.3 volts. But the USB port, which I also mentioned can be used to both program and power the ESP chip, operates at 5 volts. How is this handled? Well, most development boards that have a USB connection for power also contain something called a voltage regulator. This is a low dropout or LDO voltage regulator. It can take voltages from just above or near 3.3 volts all the way up to 20 volts or more and convert it to a steady 3.3 volts for powering the ESP chip itself. This means your project can be powered by different voltages other than USB, like maybe 3 AA batteries at 4.5 volts, or a 7.4 volt lithium battery, or even a 9 volt battery. But you need to check your documentation carefully, as all regulators aren't created equal. The two most common regulators for ESP boards are the LM317 and the LM or AMS1117. But do note that some cheap clones or knockoffs may use a different lower cost regulator that can't handle the higher voltages of the LM317 or the 1117. And none of this considers current or amp draw. A little bit more on current considerations in a bit, but just be aware that the maximum voltage and current that can be handled by the regulator may be different from board to board. Always check the specs. If you attempt to power the board by higher voltages or attempt to draw too much current, then the regulator may burn out and damage the board. Looking at these two particular boards, and it's a little bit hard to see here on the ESP8266, but both the 8266 and the ESP32 on these particular boards are using an 1117 series regulator. Next is this little chip, which is a USB to UART or serial chip. This allows UART or serial communication to the ESP chip via the USB port for programming or flashing firmware. Now, the two most common chips used are the CP2100 series, usually a CP2102, and the CH340 series. As a general rule, it really doesn't matter which chip your board has, as long as the computer being used to communicate has a matching CP2100 or the CH340 USB to serial drivers installed. Now, most modern operating systems for Windows and Mac have these drivers already installed, but I have had Windows 10 machines that were missing one or both of these drivers. But the missing drivers can easily be downloaded and installed on your local machine if needed. Again, it might be a little bit difficult to see, but in my case, both my ESP8266 and my ESP32 are both using the CP2102 USB to serial chip. Most development boards have one or more LEDs on board. Now, these can indicate certain functions like whether power is being received or maybe flashing to indicate data is being sent or received, but most are also tied to a GPIO pin so that they can be controlled via code or via the firmware. In fact, some breakout boards such as this one actually has an RGB LED on board, which means you can not only control the state of off-on, but can also control things like the brightness and the actual color of the LED. Of course, there is the USB port, which I mentioned can be used for both power and programming. Most of the current dev boards use a micro USB port, but more and more are beginning to use USB-C. The primary difference is really the type of cable you would need to connect the ESP to the computer for flashing or to an external USB power source. I'll talk about different power options shortly. Finally, most development boards have one or two physical push buttons. The first one, if present, here on the ESP32 is labeled EN for enable. On the ESP8266, it's labeled RST for reset, but pressing this button effectively pulls the voltage regulator to ground and shuts off the power to the ESP chip. When you release the button, power is restored and the chip starts back up again. Effectively, it's a reboot button for the ESP chip that doesn't require you to actually remove external power to restart the board. In addition, some development boards actually break out or tie the functionality of this button to a pin. Here you can see an EN pin on the ESP32, and it might be a little hard to see, but there is actually a reset or an RST pin on the ESP8266. If I were to do something like connect an external button to these pins, and when I press the button, it pulled this pin to ground, it would effectively do the same thing of shutting down the voltage regulator and killing the power to the ESP chip. This allows you to connect things like an external button or switch to allow you to reset your board without physically removing the power. The other button, if present, is labeled in the case of an ESP32 as boot and on the ESP8266 as flash. This button is pressed to actually put the ESP chip into flashing mode so that it is ready to accept code or firmware. Now, in many instances, the board will be placed into flashing mode automatically when you attempt to send code, but in some cases, especially with the ESP32, you may need to manually use this button to place the chip into flashing mode by holding a particular GPIO pin, in this case GPIO 0, to ground when the board is powered on. More about putting the ESP32 into flashing mode in a bit. But those are the primary components that you need to concern yourself with, and really the only thing that leaves is discussion of the GPIO pins themselves. GPIO stands for General Purpose Input-Output, and are the pins you will use to communicate with other devices. Now, input devices are those that send a signal or data, such as sensors, switches, and buttons, and output devices are those that receive a signal or data, such as displays, servos, and LEDs. Some devices may do both, send and receive data. On most boards, the GPIO pins are labeled with a number or letter and number designation. I'll come back to the GPIO pins in a minute, but let's look at a few other specialty pins and their use. Most development boards contain 2 or more power pins. You will normally find a VIN or VN pin, which is 5 volts, and a 3V3 pin, which is pretty obviously the 3.3 volt pin. There are generally 1 or more ground pins as well. Now, these power pins can be used as inputs for powering the board or as outputs, outputting 5 volt or 3.3 volt for powering other components. Note that when used as inputs to power the board, you would normally use the VIN or the 5 volt pin. This is because the VIN pin, like the USB port, runs through the voltage regulator and will provide a regulated steady 3.3 volts to the ESP chip. And as covered earlier, this also means you can use voltages greater than 5 volts up to what the regulator supports to power the board. The 3V3 pin, however, bypasses the regulators connected directly to the ESP chip. This means you need to add your own power regulation or ensure the power supply provides a clean, consistent 3.3 volts. As a general rule, you'll use the 3.3 volt pin for powering other peripherals and will power the board via the VIN pin or by USB. I'll show some various ways to power your project in a bit, but let's cover the remaining pins first. Depending upon the development board, additional pins may be added that aren't connected directly to the ESP chip. As I covered before, you can see an EN or enable pin that can be used just like the EN button to enable/disable the voltage regulator and therefore control power to the ESP chip. But the majority of the pins are just general GPIO pins. And while they're considered general purpose, not all GPIO pins are created equal, and not every pin will work for every purpose. In addition, some pins are used in the boot process. These are referred to as strapping pins, and incorrectly connecting a component to these pins could prevent your board from booting. So how do you know which pins to use for your project? The best way is to reference a pinout diagram for your particular board. This is the pinout for the ESP32 board that I'm showing. The actual GPIO numbers are listed in the inner columns. But what are all those other designations? Those are generally the default or hardware-defined pins for certain functions. As I mentioned earlier, one advantage of the ESP32 over the ESP8266 is the ability to redefine GPIO pin usage with much more flexibility. But redefining certain pins might mean it is done via software through a process called bit banging, which isn't as efficient as using the predefined hardware pins. Let's take a look at a simple example. Here I have an AHT20 temperature and humidity sensor. Actually, there are two of them just so I can show you the front and the back side. But if we take a look at the pinout documentation for the AHT20, we can see it has an operating voltage of 2 to 5.5 volts, meaning we can power it via the 5 volt or the 3.3 volt pin on the ESP32. So the VIN and ground pins here are for power to the sensor. The remaining two pins are the data or signal lines that need to be connected to the GPIO pin on the ESP32. We also happen to know this is an I2C device, which is the communication method it's going to use, but how do we select which GPIO pins are the best to use? If we look at the ESP32 pinout again, we can see two predefined pins for I2C. GPIO 21 is shown as the default I2C SDA or data pin, and GPIO 22 is the I2C SCL or clock pin. So by making these four simple connections, the AHT20 can be used with the ESP32. All that is needed is a firmware that will take periodic readings for the current temperature and humidity from the sensor and then do something with those values, like displaying on an output device or sending along to another system like Home Assistant. If for some reason you need to use different GPIO pins, you can do so, but generally need to redefine those pins in the software or firmware. And you do need to be aware of those strapping pins depending on the type of device you're connecting. But how do you identify these special pins and which ones might only be usable as input or output pins? But there are many resources out there. I think one of the best are the guides published by Random Nerd Tutorials, and I'll leave a link down in the description and in the written guide. They have sections for both the ESP32 and the ESP8266, but in addition to different board pinouts, they have these great charts down here that cover each of the GPIO numbers, whether they're safe for input or output, and any additional notes about strapping pins. For example, we can see in this case that GPIO 12 is a strapping pin, and the boot will fail if this pin is pulled or held high at boot time. Now I'll talk about the GPIO pin voltages in a minute and what high versus low means, but just note in this case that we must use caution if connecting an input device to GPIO 12 and to ensure that that device doesn't pull this pin high at boot time. Also note that some GPIO pins, like shown here, can only be used for input. The Random Nerd tutorial site also contains a ton of additional information for connecting certain types of devices or using certain types of protocols. Even though I have experience working with the ESP, I still routinely use this site for looking up best GPIO pins for a particular project or device. I mentioned earlier that the GPIO pins are generally connected directly to the ESP chip. And since the ESP chip operates at 3.3 volts, then the GPIO pins also operate at 3.3 volts. For a digital signal, meaning it's either off or on, then the signal is considered high when that pin is receiving 3.3 volts. Now, the actual voltage will vary based on the device, but generally any non-zero voltage greater than 1 volt might be considered high. But when the pin is connected to ground or receiving 0 volts, it's considered low. Analog signals are just a bit different. It scales the voltage from 0 to 3.3 volts and returns a numeric value from 0 to 4095. Now, this scale isn't quite linear like I show here. It does flatten out a bit at the top voltage range. I should also note that the analog input on the ESP32 itself is only around 1 volt, but most development boards contain a voltage divider, so the GPIO pin can accept up to 3.3 volts. So the GPIO pins generally operate at 3.3 volts. But what do you do if you have a peripheral that requires or sends a 5 volt signal? Here I have a 5 volt relay and a short strip of 5 volt WS2812B LEDs. Now, beyond the power for these devices, both of the components expect a 5 volt data signal. How can we use the 3.3 volt signal with these 5 volt devices? Well, this is where something called a logic level shifter comes into play. A level shifter can take a digital signal and shift it to another voltage, in this case from the incoming 3.3 volts to an outgoing 5 volts. Some shifters are also bidirectional, meaning it can take a 5 volt signal from an external device and shift it down to 3.3 volts for connecting to a GPIO pin. There are many different types of logic level shifters out there, but here are two of the most common you may run across. This top one is an I2C compatible bidirectional logic level shifter. It's used by connecting the two reference voltages, in this case 3.3 volts, which connects to the corresponding LV or low value side, and 5 volts to the HV or high value side. There are then 4 available channels for shifting the voltage, so 4 different signals can be shifted with this single shifter. In addition, since this is bidirectional, it can shift both the outgoing signals up to 5 volts or shift incoming signals down to 3 volts. Now, some folks have claimed these I2C compatible shifters are too slow for larger LED installations. Personally, I've used that shifter in dozens of LED projects with no ill effects. In fact, if you're interested in knowing more about level shifters in general and seeing an actual comparison of these two shifters used with various LED strips, I do have another video that you can check out later. This is an alternate shifter and is the one recommended for use with LED strips. It goes by the very long designation of SN74AHCT125N and is a quad gate buffer IC. Now, it's similar to the previous shifter in the fact that it can shift up to 4 signals. But unlike the I2C compatible version, which is bidirectional, this particular shifter is unidirectional, means it can only shift the signal in one direction, normally from 3.3 to 5 volts when wired like shown here. Regardless, these logic level shifters give you the ability to shift a data signal from 3.3 to 5 volts or vice versa for connecting external peripherals that require a 5 volt signal to the 3.3 volt GPIO pins on your ESP board. Okay, up to this point I've talked about the different types of ESP boards that are available, the primary components on most development boards, and a little bit about GPIO pin use. I've also talked about some different ways that you can power the ESP board itself. But what about if you have a larger project where you have multiple components you need to connect? What if you have multiple components that require 3.3 volts, but your board only has one 3.3 volt pin? Let's say I have a fictional project where I need to connect 3 peripherals, a DHT22 temperature and humidity sensor, an AM312 PIR motion sensor, and an INMP441 digital microphone. Now, each of these components are going to need a 3.3 volt power and ground connection in addition to any signal wires. But my ESP32 only has a single 3.3 volt pin. One option is to simply connect your 3.3 volt pin and a ground pin to something like these Wago lever nuts. By doing that, I've more or less split those signals, and in this example I have 4 additional 3.3 volt and 4 additional ground connections that I can use for connecting any peripherals. But this method can be a little bit bulky and make things a bit messy for your final project. Instead, you can use something like a breadboard or one of these prototype boards like these electro cookie boards, which are laid out just like a breadboard but allows you to create more secured solder connections for your projects. If we connect the 5 volt pin and ground to one power rail on a breadboard and our 3.3 volt pin and ground connection to the other power rail, we now have multiple connections at 5 volts and 3.3 volts for connecting peripherals. Also note this method still allows us to power the ESP board via either a 5-volt connection here on the 5-volt power rail or via the USB connection. Do note, however, that some ESP32 boards are just slightly too wide to fit on a breadboard and leave a connection of through holes on both sides. But in that case, you can either install the ESP32 on pin headers, which allows you to make connections underneath the board, or you can use something like a specially designed narrow ESP32, also called breadboard friendly, which is what I'm using here, and it's just narrow enough to allow one set of through holes on both sides. Just be aware of that when you're using an ESP32 development board. But what if we have components that need voltages other than 3.3 or 5 volts? For example, let's say we have some 12-volt LED strips. Now, sharp-eyed viewers out there are going to realize this is actually WS2812B, which are 5 volts, but let's assume for a second this is something like WS2811, 12-volt LEDs that we want to use. Now, these LED strips still require a 5-volt data signal, and the previously discussed logic level shifter can be used to shift a 3.3-volt data signal from a GPIO pin up to 5 volts for the LED strip. But the strip itself actually needs 12 volts of power. How do you handle this situation? Well, you actually have a few different options. First, you can use a power supply rated for the voltage of the higher component, say 12 volts in this case. 12 volts can be supplied directly to the LEDs for their power, but a separate set of 12-volt leads needs to be stepped down to 5 volts for the ESP-based controller. For that, we use something called a buck or a step-down converter. Alternatively, you could use a 5-volt power supply and step up the voltage to 12 volts for powering the LED strip using something called a step-up or a boost converter. Now, this may seem similar to when I previously used a logic level shifter to boost a digital data signal from 3.3 to 5 volts, but don't confuse a logic level shifter with a buck or boost converter. Buck and boost converters handle power, providing a stable voltage at a different value from the source power supply. Logic level shifters, on the other hand, handle digital signals, ensuring correct voltage translation. Logic level shifters and buck and boost converters are not interchangeable. You can't use a logic level shifter to shift up a power from 5 to 12 volts for doing something like powering an LED strip. Another option is to use different power supplies. In this case, I can use a 12-volt power supply for the LEDs and a 5-volt power supply for the ESP controller. Now, the only caveat in this case is you must create a common ground between the two power supplies somewhere in the circuit. You may get misbehaving components if you fail to do this due to ground potential differences. While it's okay to connect grounds together when using more than one power supply, assure that the positive lines from different power supplies are not connected together anywhere in the circuit. Bad things can happen if you connect the positive legs of different power supplies together. Now, this method does have the advantage of not needing any buck or boost converters, but will likely be more expensive due to the need to purchase two power supplies and probably result in an overall larger project size than using a single power supply and the appropriate buck or boost converter. Now, there are many different types of voltage converters out there. Many of them, like this one, are variable and can be adjusted to different output voltages. Some can act as both a boost or a buck converter. When you're using components at different voltages, whether you step up the voltage or step down the voltage will depend somewhat upon your project, but as a general rule, you want to do your power conversion on the side with the lowest current draw. This is because buck or boost converters themselves have a current or amp limit. For example, this boost converter, I believe, is limited to 3 amp. If we try to boost the power for a large LED display, there's a high probability the LEDs will attempt to pull more than 3 amps. This could actually damage or destroy the boost converter. In rare cases, it could even melt or fail and create a short that could start a fire. Now, I've mentioned amps and current draws a few times, but really haven't discussed what that means as related to ESP-based projects. All electronic components, even wire itself, has a maximum current or amp rating that the component will either pull when in operation or a maximum current value that the component can safely handle or pass through. Now, the GPIO pins on an ESP32 are rated for a maximum current sink of around 40 milliamps each, but it's recommended you keep this to around 20 milliamps per GPIO pin. Now, the GPIO pins are normally used for signal or data lines, which are normally very low current of just a few milliamps each. But you should always check your component specs to be sure. Current becomes more of an issue when dealing with power and the ESP's power pins. For example, The 3.3 volt pin on an ESP32 can handle up to around a peak of 600 milliamps of current, but best practices say you should limit the total current on this pin to around 250 milliamps or less for most reliable operation. Remember that the ESP32 itself and other components on the development board, like the regulators, LEDs, etc., also draw a bit of current. When in operation, the ESP32 itself will consume around 400 to 500 milliamps of power all on its own. So if you're going to do something like I showed before and connect multiple components to the 3.3 volt pin by using either something like the Wago lever nuts or creating a power rail on something like a breadboard, you have to be aware of the total current by all the components that you're going to connect, because that total current is going to run all through this 3.3 volt pin. For example, this DHT22 temperature and humidity sensor will pull about 2.5 milliamps when it's in use. Not a problem for the 3.3 volt pin. Next is the VL53LOX distance sensor, and this will pull around 20 milliamps for normal operation, but can pull a peak of up to around 40 milliamps. Next, we have a 3 volt relay. Now this can actually pull 120 to 130 milliamps when the relay is energized. Still, probably safe to be able to run that off the 3.3 pin, but it's probably getting close to thinking about powering it a different way. Finally, I have a servo here, and of course the milliamps can vary widely, but in general will draw around 150 to 250 milliamps when it's in motion, but it can actually peak at up to 650 to 750 milliamps when it's under a heavy load. If we were to combine all these together to connect for a project and connect all those to the 3.3 volt pin, we'd be looking at potentially over 900 milliamps of current, which far exceeds what the 3.3 volt pin can handle and will likely damage or destroy the ESP32. Taking a look at the VIN or the 5 volt pin on the other side of the board, recall that this is connected to this voltage regulator, and this voltage regulator also has a current limit. It's going to vary somewhat from development board to development board and based on the regulator used, but in this case the LM1117 regulator has a maximum current throughput of around 800 milliamps. And don't forget, we have to run all the components on this board as well. So to be on the safe side, I would not run anything more than about 500 milliamps max through this 5 volt pin. One of the most common mistakes I see for beginners is not taking into account the total current draw of all the peripherals in their system. I've seen a number of people that try to connect an LED strip directly to the 5 volt pin on the ESP32. So how do you handle those situations where you need to use a high current draw component, or you have a number of components that when added together exceed the current rating for one of the power pins on the ESP? I kind of showed that before when we were dealing with a situation where we have different voltages, but what we can do is we can take our power supply, split it into different legs, and run the power in parallel. To create parallel power, take the positive and ground leads from the power supply and split them, basically creating two independent branches. One branch can run to and directly power any higher current components. The other leads, or the low current branch, can be used to power the ESP32 controller. Any lower current peripherals can connect to the 5 volt power rail. Now note that I show a 1 amp limit here instead of the previously recommended 500 milliamps. This is because we're running the 5 volt power from the power supply directly to the power rail on the breadboard and not through the 5 volt pin. If we were to power the ESP via the USB port, then any current for the peripherals connected to the power rail would pass through the 5 volt pin, so the limit would drop back down to around 500 milliamps. Even when powered directly by the power supply, however, you're still limited on current when using something like a breadboard or an electro cookie board due to the small size of the copper traces. Any low current 3.3 volt peripherals can connect directly to the 3.3 volt power rail, but the current for this rail is running through the 3.3 volt pin. What if you also have high current 3.3 volt devices like a relay or a servo? Well, you can simply create another 5 volt branch off the power supply. A buck converter can then be used to step this down to 3.3 volts for powering higher component 3.3 volt devices. This particular buck converter can handle up to 3 amps of current, which is more than 10 times that of the 3.3 volt pin on the ESP. And one final note about power. The power supply itself must be rated and able to deliver the total current, or amps, of all connected components and devices. In fact, you want about 20% of headroom above the total current draw of your project. The power supply is shown with its max peak amp rating. So a 5-volt 10 amp power supply can handle a peak of 10 amps, but it's not really meant for continuous operation at that level. You generally want your normal operating current to be no more than about 80% of the power supply's peak rating. So for example, if I calculate that my project could pull up to 12 amps, I'd offer something like a 15 amp power supply. Okay, that covers the different types of ESPs, the various components, wiring, and it's a little bit about powering your board or project. So now you might know how to build a project, but the ESP isn't going to do much without some sort of firmware or code installed that tells it what to do. Now you don't need to be a programmer or a software engineer to use firmware on an ESP board. In fact, there's a lot of pre-compiled firmware out there that you can flash to your board and never write a single line of code. But there are a couple of potential gotchas, especially when it comes to the ESP32 and flashing firmware. A lot of popular firmware options, such as WLED, have moved to web or browser-based installations. This makes the process very easy for beginners. You first begin by connecting your ESP board to an available USB port on the computer. Now, this USB cable must be a data cable and not just a charging cable, but the type will depend upon the available type of USB port available on the computer and the type of USB port on your ESP development board. As mentioned earlier, most development boards use micro USB, but development boards that use USB-C are becoming more common. When connected to the computer, a new COM port should appear. Notice this one even says the CP2102, which we happen to know from earlier is the USB to UART chip that's on our ESP32, so we know that this is the right COM port. If you don't see a new COM port, then the odds are the computer you're using does not have the USB to serial drivers, which I discussed earlier. Many web installers like WLED will actually assist you with adding the missing drivers if you don't have them. Once connected to the correct COM port, in most cases you just click install and the installer will connect to the ESP and start installing or flashing the firmware. For most ESP8266 and a number of ESP32 boards, that's all you need to do to get the initial firmware installed. However, some ESP32 boards require that you manually place the ESP chip into flashing or bootloader mode before it will accept the firmware. Recall the buttons I referenced in the section on the primary components of the development board? Well, these buttons can be used to put the ESP32 into flashing mode. Now to do this, GPIO 0 must be held low or connected to ground when power is applied to the board. There are a couple of ways to do this. Recall that the boot button is connected to GPIO 0. So I can just press and hold this button down while I plug in and apply power via the USB port. When power is applied, I can release the button and the board should be in flashing mode. But this can sometimes be tricky with only two hands. If your development board also has an enable or a reset button, we can use this in combination with the boot button to put the ESP32 into flashing mode. Recall that the enable or the reset button is actually connected to the voltage regulator and will pull it to ground when pressed, effectively cutting off the power to the ESP chip. When the button's released, power is restored. So it's more or less a reboot button. So in this case, we can go ahead and connect our power, but then you want to press and hold the boot button while you press and release the enable button. That will restart the board with GPIO 0 connected to ground. I can then release the boot button and the ESP32 should be ready to accept firmware. This can be a little bit tricky until you get used to it, so you may have to try a couple of times. If you see an error message from the flashing utility about a failure to connect or communicate, and you're sure you've selected the correct COM port, it's often due to the fact that ESP32 isn't in flashing mode. Well, what about installing firmware that doesn't have a web-based installer, like maybe firmware that's in someone else's GitHub repository? Well, if they have releases, you can always check there, and if you come down under the assets, you might find a compiled bin file. If present, all you need to do is download that file, and you can use a number of different desktop utilities, or even the web-based ESP tool to flash the firmware. Now, most flashing utilities work in a similar manner. You're going to connect to the COM port where your ESP is connected. Then you simply select the firmware file that you wish to flash and either click the Upload, Flash, or Program button. Even if the GitHub repo doesn't offer a compiled version like this one, but only the source code, Compiling your own really isn't difficult. In most cases, you don't need to be a programmer or a software engineer. In fact, I have a completely separate video on setting up and using the Arduino IDE for non-coders, which covers both the setup of the IDE and shows how to compile and flash code, even making minor changes to things like GPIO pins if necessary. Well, the process is pretty similar, and I've got other videos where I walk through the step-by-step process of installing things like WLED or Tasmota onto a device, so I'm not going to cover that here, but most firmware will contain at least basic instructions for how to install the firmware onto an ESP8266 or ESP32. Always be sure to check the documentation. Of course, the ESP isn't the only type of microcontroller out there. There's the whole Arduino family of microcontrollers among others. And if you need even more processing power, you can step up to something like a Raspberry Pi. Now, while there are significant differences in these boards, they also have a lot of similarities, such as the use of GPIO pins and voltage and current requirements. So a lot of the topics in this video can be applied to those types of boards as well. I'll be back soon with more videos on DIY electronics and home automation. But until that time, I'd like to say thank you for watching, and I hope to see you again soon.